Okay, I think since everyone else is doing it, we'll get started as well. I'm going to try and shout as loud as I can without shouting over everyone else in the room. So please tell me if you can't hear me, and then I'll shout louder at you. So this is Delicious Dome Mapping. My name is Michael McKellar. I'm from Scotland. I'm going to bore you with a little bit about me before we dive into what we're actually doing here. Then I'd love to hear a bit about who you are, why you picked this class, and what you're hoping to actually learn from it. So I recently moved from the US back to the UK. That's me and my lovely wife at the San Francisco Bridge. I was working as a professor at practice where I was teaching touch designer as well as developing my freelance. I had the fortune to work for some amazing companies on some pretty incredible experiences. One of the most recent was for HBO and Game of Thrones, where we built this, or I was involved in building this immersive Game of Thrones experience using touch designer, where you went through a bunch of Game of Thrones inspired experiences. I also teach workshops like this one around, this one was recently in Texas, where we were looking at how to work with depth sensing cameras to track things. I run a company called Program for People. That's an online teaching resource. You might hear me on YouTube whining at you if you ever search for touch designer tutorials. We cover everything from the basics all the way through to really complex things like we're going to do today, that is projection mapping and pixel blending. As part of that, I have a commercial arm called Learn in 10, where we sell long-form tutorials online as well. My bread and butter is I'm something called a technical lead. So in Glasgow, I worked for two companies called Solus and another called Sublime, where we developed immersive projection domes like this one. So since about 2015, I've been working in the projection dome world, and most of that is based inside Touch Designer, where we build things like freestanding 4-meter domes, all the way to this product is it's called the Situ. It's in partnership with a company called Cirque de Bicouza, and this is yeah. So I helped design and build that. But we'll come on to that in a minute, don't worry. So this is an 8-meter freestanding dome that uses 12 projectors all blended. This one does use an automatic calibration system, but today we're going to look at the bread and butter of how to do it without fancy cameras and really expensive technology. I said I recently moved. I now work for a company called Marshmallow Laser Feast. That is the most incredible name to ever say to someone on the phone, where I am the technical lead and we are building physical virtual experiences. So combining the virtual and physical together with deformable tracked objects. So right now my office is like a frat pool party, but we are doing some of the coolest stuff I've ever had in my career of doing. I love it. So please ask me to bore you about this later if you're interested. So today, why are we here? Delicious dome mapping. I said I've been working with domes for a while, and over that time I've built up a bunch of really weird skills and techniques to get projected images into domes. And this class is going to go right back to the basics on what does that mean and how do we do it. So we're going to build a piece of software that I've used for a long time, built from all that knowledge, and I call it the dome mapper. So we're going to learn how to build a virtual dome, take a photo of that dome, or have a camera in that dome, and then project back into that virtual dome, manipulate that captured image, and then project into a real dome somewhere. It was my goal. I was hoping to have a dome here, but they're really hard to transport, and I couldn't build a small enough one in time. So we're all going to have to use our imagination a little bit, I'm sorry, but it should be really good. Importantly, this is a link to a Dropbox folder where right now I have a single 8K by 8K calibration grid for you to all grab and download. So please hop onto it and download it. Like that? Sorry. Just behind you. So it is about a 4 meg file because it's a raw PNG, but it's a calibration grid for an 180-degree dome that you can use in anything you need. It says my name over it, so please use it commercially everywhere that you go. Okay, super. So just so everyone knows, as I said at the start, I am Scottish. I have a tendency to speak very fast and slur my words. So if something hasn't come across, please just stop me and tell me to go over it again. There are going to be parts where we're having to program. It will obviously be on the screen, but if you're not natively a programmer or you're new to Touch Designer and need more on the Python, please ask me to just slow down. Every hour or so, I'm going to try and stop us, take 5 minutes so everyone can go and get a drink and decompress from the mind explosion. So please take that time to ask any questions that you've got, and we'll go from there. So let's have a look at what we're actually here to build. So this is effectively the software that we could end up by the end of today. We only have 3 hours. This took about 13 to make, so we're not really going to get to this stage. But ultimately, it's a full dome mapping kit. It allows us to make a dome of X meters in size. So if I bring up a 3D preview, we can make a 2 meter dome by 2 meter dome by 2 meter dome. We can orientate it over someone's head, say it was 90 degrees. And then it allows us to add projectors to that scene. So I can add 2 projectors. And now if I look at my preview, what we'll see is that I have 2 different projectors in that space. They appear like cameras because in Touch Designer, that's what we're actually going to use. We're going to use cameras to look at a virtual dome and then use what they see as our projector's output. And that'll make more sense as we start to develop, but basically we use a funky combination of lights and cameras to create a virtual and a real projected image in the same space. We then build a bunch of pixel mapping tools. If I look at projector 1, so this is what projector 1 is currently seeing inside our dome. It's pointing away from it stupidly, but we can then, like a stoner, manipulate it in a variety of different ways so that we can start to align images inside our canvas. And that is what our dome is currently projecting. Let's move this projector slightly so we can actually see it. So there we go. Now the red projector is sitting on the edge of my dome, pointing into the middle of it, and it's now exposing this part of the dome surface. Now, if I was to configure projector 1, we can see I get much more of its projected image. We can manipulate the pixels slightly, mask the edge, and suddenly we're creating blended overlapping images. And that is, in principle, what we're going to build today. We're going to look at how to make those cameras, project it into a dome, and then make these manipulation tools from scratch so that you understand what you need to do to implement it into your own dome needs. So if everyone's got the file from that Dropbox folder, let's start a new Touch Designer. So in this, we're going to use general primitives inside Touch Designer to make our dome, but you could quite easily use a 3D model that you've made, like an OBJ or an FBX, and bring it in and then map onto that. Kind of the same way if you were going to use something like CamSnapper, for those of you that have projection mapped before, but we're going to do all the work ourselves. Okay. So first thing we need to do is make our dome. So let's bring in a sphere. SOP. Now, the problem with the sphere SOP is it's a full circle, so we need to cut it in half. And to do that, we're going to use the clip SOP. Now, by default, your sphere is going to completely disappear, and that's because we're using a mesh. And to get a cleaner cut or a cut on the mesh, we're going to change our sphere's primitive type to be polygon. And then in our detail tab, we're going to turn that way up. I'm going to actually set it to about 100. And that's just going to give us a much nicer resolved half circle. I am using 166000. Did you bring in a sphere or a circle? Which operator are you currently selected? Yeah, it's on the sphere. We got it? We good? Okay, so what we've just done is we've made a half dome. Now, what we need to do is we need to apply a texture to that in the right way. So if by default we apply a material, and then you go and get that image that you downloaded and drag it into our window for us. And then because of the size of that image, I'm just going to lock it into the Touch Designer file just to help us load it if for some reason we need to restart. I'm going to apply that top to a constant matte, which lets us use the texture as the material for our dome. And then I'm going to apply it to the material SOP. Yes. No, that's fine. Okay. Don't worry. Right, okay. So the first thing we did is we popped in a sphere SOP. Have you used Touch Designer a lot? Yeah. So we're making just a general 3D ball. And then we changed its primitive type to polygon so that we can cut it properly. We pass it into a clip and don't change anything in that. And then we pass it to a material SOP, and that allows us to apply textures to the 3D shape. I dragged in that alignment grid that we got from that Dropbox link. We attach it to a constant material, and then we attach that material to the material SOP. So what we should have now is something that looks a bit like this. And we'll notice that it's super messed up because it's still trying to apply the the full dome texture to the original sphere's texture coordinates. So between the material and the clip, we're going to add the texture operator. Yeah, sure. So that's the Dropbox link again for those of you that need the texture. Perfect. Okay, so we've added our texture between our clip and our material. And in here in texture type, we're going to come up and change it to fisheye 180. I'm just going to double check something, whether I'm telling you to do this the wrong way around. Sorry, I've got myself confused as to applying the texture properly. Okay, I'm going to change the order of these operators slightly. I connected them up the wrong way. So we want to connect our sphere to our texture to our clip, and then our clip to our material. And then in our clip, we're going to change our direction from being 0, 1, 0, 0 to 0, 0, 1. And what that's going to do is when we change the direction of this clip information is we change it from cutting the sphere through the y-axis to cutting it through the z-axis. So again, my apologies for that. It's sphere, texture, clip, material. The texture is, you change it to fisheye 180 degrees. It should be the second from the bottom. So does everyone have something that looks like this? So that should be when I changed it to polygon and turned detail up to 100. Yeah. And again, the thing we did on the clip was change the direction from 0, 1, 0 to 0, 0, 1. Oh. Go back to the Dropbox links for me. Can you go to where you downloaded it? All right, and go back to Touch Designer. And then click the plus. Go to click it again and open it from there. Click the exclamation mark. It should still resolve though. It should still show it. What's happening over there? Are you good? Are you okay? Okay. Has everyone got the dome now? Perfect. So the problem is if I activate my material viewer and start to rotate it, we're looking at the dome from the outside in, which means although our texture looks right, if we go inside our dome where we're going to be doing all our work, it's back to front. To fix that, what we're going to do is go back to our texture and change the scale to be -1, 1, 1. Effectively, we're rotating the texture on the x-axis to apply it correctly inside our virtual dome. So that's the texture SOP, change its scale to be -1, 1, 1. I don't know. Okay, thank you. Okay, so now inside our material, we can see that we're inside our dome and we've got it the correct way around for our texture. So the next thing we're going to do is we're going to turn this into a piece of geometry. So I'm going to right-click the outlet of my material, come up to Comp and select Geometry. And that's automatically going to build the geometry using the SOP input. If you end up with a torus, you're going to have to go inside and add an in-SOP. So the easiest way is right-click, comp, geometry. And that brings it from being in the SOP world into the geometry world. So now, so that we can start to see things, I'm going to split my UI a bunch of different ways. Because we're working in 3D, I'm going to split my UI into 3. I'm then going to change the top right to be a geometry viewer, so I can now see my lovely sphere. And I'm going to change the bottom right to be a panel viewer. Okay, so right-click the outlet from your material, and then go to geometry, and it'll automatically connect it for you. Okay, has everyone got the geometry made? Okay, and now really importantly, we need to give this a name so that we can reference it later. So I'm going to call my geometry specifically Capture Dome. Capture Dome. You don't need to copy the name exactly, but as long as you have a name that you can reference specifically later. And now we are going to add a render top so we can see things, and a camera. So when you put a camera inside Touch Designer, by default it sits at 5 back on the Z. But because our dome, we cut it on the Z axis, it now means that our camera is outside of it. So what I'm going to do is I'm going to rotate my Capture Dome geometry by 180 degrees on the Y. So now in my geometry window, I can see that my camera is pointing into the middle of my dome. Now, because we are working inside the main project folder, if I right-click my render and add an out, what this means is my panel for project 1 will automatically be populated by that texture. For those that aren't overly familiar with Touch Designer, that's because we're inside a container, and the container's background is set by default to out 1. So in the top right, we can see our world in 3D. In the bottom right, we can see a 2D version of a camera pointing straight into the dome. And apart from rotating Capture Dome, I've not had to change any settings. By default, it's already running as we need it to. Everyone got that? Okay, so what we've just done is we've made a dome, and then we put a camera that's looking straight into the center of that dome. Now, this camera that we've made, we're never actually going to use for projecting. This is now purely a reference tool for us to see what's happening inside our surface. What we need to do is we're going to make a projector. And that projector is going to be a camera, which sounds like I'm crazy, but inside Touch Designer, it's going to be a camera that's then going to have a render that will become its own projected texture. So what we're going to do is we're going to add another camera, and we're going to call this one projector_0. Again, the name you make doesn't need to be the exact same. What does need to happen is you need to have a 0 at the end of it. That's all that I care about. because we're going to use numbers specifically to help us build many of these later on. And I'm going to change this translate to be 0. And what we'll see up here is I've just put a camera in the dead center of our dome. We're then going to make a render. And again, we're going to rename this render in line with that same naming convention. So this is going to be proj render underscore 0. Now, instead of all geometry, what I'm going to do is I'm going to tell it to get just capture dome. And I'm also going to tell it to get the camera of projector 0.
Maybe do that again.
Yep. So after we've made our geometry, we added 3 nodes and we didn't change anything to them. We added a render texture, or a render top. We added just a base camera component, and then we attached that render to an out.
Don't do it again. Just go through the steps.
Yeah. So a render top, attached it to an out top, and then when you add a camera, the default name will be camera 1, and that'll automatically make all the connections for us. What's on the screen? Oh, sorry, I thought it was that part you were asking about. So yeah, we're going to make a second camera. Yeah. So, change the name to be anything you want, and at the end it needs to have underscore 0. You're then going to add another render top, and again, call it anything underscore 0. Inside that render top, we need to tell it to see only the original dome geometry that we called capture dome. So I'm just going to drag and drop that geometry onto the top parameter. So literally pick it up and place it down. And I want the camera to be projector 0. We're then going to add that render to a null and just leave it over there for now. And next, we want to add a light. Now, a light might seem counterintuitive, but this is what's actually going to be our projector. That light I added, in the same naming convention, I'm going to call this proj light underscore 0. I'm going to set its translate to be 0. And then finally, I'm going to parent the camera we made to the light we made. So from the bottom of this projector 0, I'm going to plug that into the top of projector light 0. And what that means, now anywhere this projector goes, rotates or moves, this light is also going to be with it. Yep. So you're going to add a light, change its translate to 0. So it should have a translate of 10, change that to 0. and then parent and child them together by dragging from the bottom of the projector to the top of our light. Yeah, bottom of the projector to the top of the light. Can you do me a favor and just check the texture application on that? Okay, so as of now, we've almost got enough to start taking an image of our dome and sending it somewhere else. But we need to make sure that our projector and our light are seeing the same thing and the same ratio. So what I'm going to do in my light parameter tab of the light is I'm going to change it to be a cone. So in the light, change its light type to be a cone light. And what this does is it gives us something that we can angle more. And what we want to do is we want to match the angle of this light to the angle of our dome, to the angle of our projector. So the camera that we set up for our projector has something called field of view that dictates how wide an angle it sees from its lens. We are going to take this parameter and attach it to our projector light. And to do that, we're going to change our cone angle parameter to be an expression. And we're going to write an expression that goes and gets the field of view of our camera. And to do that, I'm going to type operator parentheses speech, projector underscore 0, speech parentheses, dot par, dot FOV. Okay, so has everyone got that to link? It should now give you this cone angle, should now become the field of view of your camera. We want to change cone delta to be 0, and we want to change cone roll-off to be 0. And at the very bottom of that page, there's something called projector angle. Yes?
Can you show how to make that expression without typing it?
I just type it.
But is it not, can we just copy and paste it from the where was it?
So it's in here, yeah?
Right click on the parameter, copy parameter.
It's the camera view field of view. And then, so inside our light, we're going to take that reference that we made, we're going to copy it, and we're going to paste it into the projector angle field as well. So now cone angle and projector angle are the exact same value, referencing the camera's field of view. The cone angle and the projector angle are the same. So these are both in your light that is connected to the camera. Whereabout did that happen? So do you not have it as a reference? That's just whatever we're going to change that in a minute, don't worry. That's just whatever that was set to from fiddling around with it. It can sometimes change the way that the texture is applied after you cut it. Because the way that the sphere resolves, we have a perfect seam on that line that we've cut it on. If your detail's too low, you can have lots of jagged edges to your texture. Okay, now in our camera's field of view, we're going to set that to be 80. It's an arbitrary number. Depending on what projectors you're using inside your actual dome, this is something that you might need to calculate. But in general, a short throw projector can have around an 80-degree field of view. So that's what we're going to stick with for this example. Is everyone okay on that side? I changed the camera's field of view to 80. So the throw ratio, I'll put something in the Dropbox link after the class, but you basically use Pythagoras to work out, you use cos, inverse of cos to work out the angle based on sides of lengths and stuff. Okay, so now we have a camera and a light in the same position at the same angle. We're now going to use what our camera sees in the projection field of our light. And inside the projector camera world of Touch Designer, that means that we're basically going to use the image from our camera as the output for our light. So click on your light, you'll see a field called projector map. I'm going to pick up null 1 and put that into projector map. Now, when you do that, you should get an exclamation mark on your light that says you've made a Cook loop dependency. So inside projector render 0, I'm going to delete the asterisk in the light field. So basically, we were asking Touch Designer to render a light that it was trying to capture from the same camera, which is impossible. So we tell our camera's render to stop seeing that light altogether. So the light now has a projector map of null 1. And projector render 0 now has nothing in its light field. Pardon? I just copied and pasted the same expression from above. Okay, so now we've got a camera seeing our virtual dome. We need to make somewhere for our light to go and be received. So what I'm going to do is I'm going to copy and paste the material and capture dome that we made earlier. So I'm going to select it, I'm going to copy it, and I'm going to paste it. And I'm going to change the name of Capture Dome 1 to be Mapped Dome. And in the constant 2 that we just pasted, in the constant tab, we're going to click Apply Projection Maps. So what should happen is the entire constant material and mapped dome images should go black. And because what we've just told Touch Designer to do is receive any lights that are projection mapping, which we've just set up, and then display them in the render. But this system can't do that. It's only when we get to the render stage it's going to be able to resolve that for us. So in render 1, the one that's connected at the bottom that we very first set up, in the render tab, we're going to tell it to see only mapped dome. And what we should start seeing in our panel, I'll go over it again in a minute. What we'll start seeing in our panel is a small, slightly squished rectangle. Okay, so to go over that once more, we copied and pasted our material, our constant, and our capture dome. We changed the pasted capture dome 1 and called it mapped dome. And then in the new constant that was made, we ticked apply projection map. Did you get that?
Did you change the geo for capture dome?
Yep.
Did you change the name of geo1 for capture dome?
Yeah.
Okay, yeah, you can see that. And also, this material 2, map dome, and then constant 2 I don't have. So.
Okay, so select constant 1, material 1, and your geo 1, and copy and paste them. So just Control C, Control V. And then once that's in, I want you to click the new constant that you made and tick this box called Apply Projection Maps. In the render at the bottom, render 1, pick up the new geo that you made, so yours should be called Geo 2, and drag it into the geometry section. Yep. So do you see this? No. Okay. It's just apply projection map.
It's a function of the apply projection map here.
So give me 1 minute. So what we'll do, just while we sort some people out with that part, everyone take 5 minutes, go grab some water if you need some, decompress. Okay, let's pick up. So what we have now is basically we're done. We can pack up, we can go home, it's finished. So what we have is we have a camera on 000 looking into our dome. And what we're seeing in the bottom right is what that projector would be able to throw onto that dome surface if it existed in that space. So we have a field of view of 80 degrees. Our camera is on 000 in a meter dome. So it's 50 centimeters from the surface, throwing at 80. It means that in the bottom right, that is all that it would be able to project from that space. So if I do something like move my camera, don't worry, you don't need to do this, but my projector 0, if I was to move it, say, over to the right, so I've moved it over to the right edge, I'm going to rotate it back into the middle, like a common dome configuration would be, a camera or a projector mounted on the edge of your ring. Rotating it back in by about 45 degrees gives us what the projector from that space would be able to throw onto that surface. So what we're starting to see is that if we were able to mirror like for like exactly a projector on 0.9, so it's 10 centimeters away from the edge of the surface of my dome, pointing at 61 degrees into the center of my dome, that is exactly what it would be able to throw onto its surface. But the reality is in real life, you're never going to be able to attach a camera or a projector exactly where you're modeling it in the virtual world. So what we're going to build is a bunch of tools that allow us to just nudge pixels ever so slightly, so that if there is, say, a discrepancy where a camera and a projector are, that we can adjust it with some toggles, we're going to use a really complex mesh underneath a really simple mesh to basically drag and drop a grid around. And that'll allow us to move pixels in space. So if the reason we added the null is between our render and our null 1, we're going to add a bunch of stuff. So first thing I'm going to do is I want to show you an example of you're never going to have just one projector in your dome. So I'm going to add a channel mix top. So I spread out my null and I just right click on the line and I click insert operator. So I'm going to add an operator into that chain. And what we're going to do is we're going to change our channel mix to be 0 red and 0.5 green. So we should get a nice blue image thrown onto our dome. Then I'm going to copy everything, my light, my projector, my render, my channel mix, and my null. I'm going to copy and paste it. And because you all stuck to the naming convention I told you about really strictly, it means that everything's going to work for us naturally. So all our projector zeros, so our projector 0, our light 0, our render 0, have all become light 1, projector 1, and render 1. And in the chan mix, I'm going to do the exact opposite of what we just did. So I'm going to have a red of 1, green's going to stay 0.5, and I'm going to change blue to 0. Everything in that chain that we made, so projector, light, render. So the reason we use channel mix is because when we're trying to project on two projectors on top of each other, we need to know where they overlap. And now that we've changed our channel mix to be the invert of one or the other, it means that where our projectors overlap, they will generate pure white. Everywhere else, they'll generate just their natural colors. So play about, it doesn't matter where you move them, but move your projectors somewhere in your scene. I'm going to put mine on opposite sides and do the opposite rotation. So I've got a projector on either side, both pointing towards the center of my dome. And down here, we can see I've got one that's blue, one that's orange, but where they overlap, it's perfectly white. And in my virtual environment and my physical environment, it shows me where my two projectors would lie on top of each other. Now, I realize I just said a lot of you, so I'm going to walk around and make sure that we get that set up. Okay, everyone seems to be at that point. All we've done there is we've basically allowed ourselves to see where our two domes' beams cross in space. What we would need to add here is we need to think of some way to make that less of a harsh edge and ultimately make them blend so that anywhere that there is white, there's 50% of one projector and 50% of another projector making that. And that's where we're going to add all these pixel nudging tools that I was talking about. So for now, we're going to move the bottom projector just out of the way and forget about it. And we're going to focus on projector 0. So that's projector 0, light 0, and render 0. And we're going to be using a bunch of UI tools here. So we're actually going to set this inside a new container, just so that we can keep it tidy because there's a lot going to go on, and so that we can interface with it later when we need to. So I'm going to right-click, insert an operator, and I'm going to insert a container comp. Now, when we do that, it means the container is going to automatically be set up with an in and an out for us. And we're going to just need to connect our channel mix 1 to the in that it made. So we're just making a container, attaching channel mix 1 to it, and the out. Now, one of the questions I was asked just before we dive into this next section was, where does the projector's aspect ratio come into this? And that all comes from our render. So by default, a render has a resolution of 1280 by 720. For a standard projector, we want to set that to 1920 by 1080. And obviously, if you had like a WQ, you change it to 1920 by 1200. And the reason we do that is because both the light comp and the projector comp don't conform to any of these aspect ratios. If you change your projector comp, it keeps its field of view, but it starts to show us stuff that our camera would never actually be able to see. It's the render that does all the work for working out what the projector can and can't see. So change the resolution of your render projector 0 to 1920 by 1080. And we're just going to pretend that we have a 16 by 9 standard projector in front of us. I'm going to change the name of my container that we just made to be rough map. So, yes. So that's in the render coming from your camera. In the Common tab, change its resolution to be 1920 by 1080. All we're doing is making the content inside this window full HD. And then once you've done that, change the name of the container we made to be rough map. So what we are going to do, if I load the other example, and I go to the rough pixel, what we're going to do is we're going to make a grid that has handles that we're able to move that manipulates the image underneath that grid, manipulates the image underneath on a grid. But I have a very low resolution grid on top here. This is, I think, 16 by 9 it looks like, or maybe less, 9 by 7. But in reality, I've got a grid that has 400 different manipulation points underneath it. And we're going to use a special SOP called the lattice SOP to allow us to manipulate super high resolution or high density meshes using a lower density one like this. Now, there's many reasons to do that, purely because if I gave you a grid with 400 points to pixel map with, it would take you hours, if not days. So by using the power of the lattice SOP, we can use this low resolution mesh to control all of these 400 points underneath it using maths, effectively. And that's what we're going to do. We're going to build a variety of different pixel mapping levels. So this one's rough. We'll do one that's fine. And then we'll use the same theory to allow us to move where the corner of our images is and ultimately mask the edge of each projected image. So inside rough map, we're going to go in, and by default, you should have an in connected to an out. We're going to stretch them far apart and disconnect them. And in the right-hand panel window, I'm going to click the little / and change it to be rough map. So you should now have a black square. So that's visually, I'm going to change this to be inside the rough map container we just made. So the first thing I notice is this is a square, and our screen is 1080. So I'm going to change the width and height to be whatever the width and height of your native UI is. In my case, it's 1920 by 1080. No, so this comes from your screen where you would have your control UI. The projector is separate. So for example, if MacBooks have really bizarre like 2560 by 1440 resolutions, whatever that is. So rough map now has a width of 1920 and a height of 1080. For the sake of this demonstration, if you're using a MacBook, just set it to 1920 by 1080. Because when you go into perform mode, it'll be a 16 by 9 window. Okay, inside rough map. First thing we're going to do is we're going to create that super high density mesh I was telling you about. but we're going to use a bit of funky scaling to do that for us. So what I'm going to do is I'm going to make a grid SOP. And the grid SOP by default is a mesh, which is good. And it's also got 20 rows and 20 columns, which is also good. With that, I'm going to attach it to a material, if I can find it. And then I'm going to attach it to a null. So I've got a grid that is just a square. I've got a material, and then I've got a null.
Make it a bit closer.
They were shouting at me for it being too, because I'm yelling. Okay, now the same little trick we did before. I'm going to right-click the outlet of my null and turn it into a geometry comp. So what we've basically made is we've made a grid that has 400 little dots inside of it. We've said we're going to add a material that we've not done yet. We've used a null that's just a nothing SOP, and then we've turned it into Geo1. Okay, now we're going to add a null comp. We're going to use a null to do all of the scaling inside of our scene for us. So we're going to add a null, and we're going to need to do a bit more programming here, because I want to make the scale of this null the same as the aspect ratio of our projected image. That's why it was important we went back and changed that resolution. So in the X scale, what we're going to say is we're going to say go to in1 and get its X aspect ratio, or its width, which in this case is 1920. So we're going to type operator, or OP, parentheses, speech, in1, close speech, close parentheses, dot aspect, width, capital W. So operator in1 dot aspect width. And you can see we've now got the little gray linking line, and our scale is 1920. I'm going to do the same for the Y scale, but this time I'm going to say aspect height. So in1 dot aspect width, in1 dot aspect height, and that gives us a null that has an X scale of 1920 and a Y scale of 1080. And inside this geometry that has our grid in it, it looks like a square, but we're going to use the null to parent it. So take from the bottom of the null we just made into the top of the geo, so that there's the little parent-child line. And what that's just done is that's turned our 400-point square into actually a 400-point rectangle. And to visualize that, what we're going to do is we're going to add a camera. We're going to add a render top. And we're going to add a null to that render top. Now, everything will be black for now. I just want to make sure everyone gets this set up so that we can move on to the next part. Okay, so now that we've got that camera set up, what we need to do is we need to change our camera type from being perspective to orthographic, because we really, importantly, need to capture the right amount of pixels in the view without any field of view distortion in them. What was your question, sorry?
Just where to drag the null.
Okay, so what we do, if this is the one up here, I'm going to move it just so visually, but we're actually going to take this bottom one into the top one. And that, if I look at this, that's right. So what that's done is basically now saying anything below this is a child, and it's going to inherit any properties from here.
Yep.
So we've turned your scale of 1:1 into an actual scale of 1920 by 1080, which means it's going to be pixel perfect for us. So to do that, we're going to click on the cam one that we made. We're going to go to view, and we're going to change its view to be orthographic. Now, by default, the orthographic width is 2, but we need that to be the exact same as the aspect ratio of our image. So I'm going to type the same piece of code. I'm going to do operator in1.aspect width and make it a 1920 wide camera. And what we start to see is our rectangle that has no texture on it appear in the camera's view. Now, remember I told you that cameras don't adhere to aspect ratios properly, but because this is orthographic, it means that the width is going to be right. So we can see that our image is going from one edge to the other edge perfectly, which is what we need. It is operator in1.aspect width. And now, so that we can see whether this is right or wrong, I'm going to turn the image coming in into a material and use that on our geometry. So I'm going to make a constant mat, drag and drop in1 on top of it, and then drag and drop constant 1 onto material 1. So make a constant material, apply null 1 to the constant, and then the constant to the material SOP. It's to do with, we're going to do a bunch of stuff later where we're going to use different materials on different geos. I don't know how it would work if we applied the material inside the geometry. I don't know if it would inherit the meshes deforming properly, I think is the technical answer, but I just don't know. Okay, so we've got our texture. We should see this really squished version of it. But if all things have gone well, by the time it gets to our render out, we should see a like for like of the image that's coming in null 1. And just so that I can see it in the bottom right window, I'm going to scroll out one level. I'm going to remember the name of that null, actually. So coming out of our render, I have an operator called null 1. I'm going to call that output. I'm going to come up one level. And in the rough map container, in its look tab, I'm going to say ./output. And that means make the background of this container a node inside called output. That's what ./ means. It says go inside of this container. And don't worry about the red X at the top right. That's just because we have an out node that doesn't have anything connected to it yet, but we're about to get there. Okay, recap. What have we done? We've made a container called roughMap. Inside of that container, we've made a grid of 400 points, given it a material that is our so what the camera is seeing in our dome, turned it into a geometry, and then used some funky scaling and an orthographic camera to make a perfect width version of the image that's coming in. So right now, we're doing nothing to it apart from wasting resources, but we're going to do a bunch of manipulation to this grid so that we can warp the output image. What I want you to do is I want you to copy and paste the camera, the render, and the output nodes that we have. So I'm going to copy and I'm going to paste. And I'm going to move the pasted version up to the top right and connect the new output to the out. So our camera, our render, and our output, copy and paste them, and make a second version at the top right. In that render that we made, take Geo1 and make it the only geometry it's seeing. So instead of an asterisk, make sure that the new render says Geo1. Now, the reason that we're making two different cameras is because this one down here, the first one that we made, is going to be our interface camera. It's going to be the one that has all the dots on it, that has all the manipulation and the grid visible. And if I show you back in the other example, because we have dots that go all the way to the edge, if I used the same image, it means I'd be trying to drag a dot that was half off the screen. So we're going to scale one of our camera views slightly, just so that we can get this slightly ringed effect. So in camera 1, the original one that's not connected to anything but output, inside of its ortho width, I want you to times that by 1.1. So what you should see in the window on the bottom right is you now have the image with a little black ring around it. So by making the ortho width wider, we now have this border that means we can see all the edges of our texture. Okay, so now we've got our super high density grid. We're seeing it from a camera that is orthographically 10% wider than our texture. So we get this nice black border around the edge. What we need to do now is build the less complex mesh over the top of our original lattice, our original grid. So what I'm going to do is I'm going to double click and I'm going to add another grid. So I've got grid 1 that is 20 by 20, and I've now made grid 2, and I'm going to make that way smaller. I'm going to make that one about 9 by 7, let's start with. So rows 9, columns 7. It gives us a lot more control over what we can and can't do. So there's basically we're going to render pick where the mouse is within the panel, which is a super intensive system. So when we build it ourselves, we get the ability to turn it off, but we're effectively making a version of Stoner, yes. Okay, so I've got grid 2 that is 9 rows by 7 columns. I'm going to attach that to a material. And again, I'm going to attach it to a null. And what I'm going to do is I'm going to turn that null into a geometry the same way we did before. And once we've made it, remember to parent it to our null again. Otherwise, it won't be the right size. So grid 2 with less rows and less columns, to a material, to a null, to a geo, and make sure to parent that geo to the null. So your screen in the bottom right should go black because we basically just put a texture or a 3D shape over the top of the original one. And to make sure that actually happens, we're going to change our Z translation to be 1. So Geo2, make it Z translate 1. Because we're using an orthographic camera, we're not going to see that depth, but it means that we can start to layer our grid on top of our image properly. And now the exciting part, we want to see our grid. So we're going to add a wireframe mat. And that wireframe mat, you're just going to drag and drop onto material 2. Yep. So it should by default go into camera 1 because camera 1 will be looking for all geometry. But we don't want to connect it to render 2 at the top. So you should have camera 1 and render 1. If you click on render 1, make sure that its geometry is set to an asterisk.
Oh yeah, it's asterisk, but this new geo that is created after the null is linked also with CM1.
No, it should be linked to the null. Okay. Just before I run around and check that, our grid, the second grid that we're now visualizing with a wireframe, is almost there. We can see all the points that we're going to have, but we've got this crossbeam that we don't want. So I'm going to change the grid type to be polygon, and then I'm going to make the connectivity rows and columns. It's really important we do that. So polygon and rows and columns rather than quadrilaterals. And what that means when we change it from being quads into rows and columns, it means even when dots get close together, it won't solve them into 4-point triangles or with triangles crossing the boundaries. Okay, so now we've got a super high density mesh, and now we've made a lower density grid on top of it. What we need to do is we need to create points on that grid that we can go and grab. So we'll do this bit, and then we'll take another 5-minute break, and then we'll move on to actually manipulating this grid. So we're going to use a little bit of geometry instancing to allow us to create all the points without us doing any hard work. But the first thing I need to get is I need to get a list of all of these points, make them a table, and then make a copy of that table so that we can properly send references back and forward between two different SOPs. So between grid and the material, I want you to insert a DAT2 SOP. A DAT2 SOP. So for those that have not done much SOP development, what we can do is we can turn a mesh like this grid into data points, change those data points and pass them back in using the DAT2 SOP, and to manipulate the original geometry by a table. So first thing I'm going to do is I'm going to turn my grid2 into a table by inserting a SOP to DAT, so the pink one. Now drag and drop grid2 onto that new pink DAT, and we'll get a big grid of data that are basically all the X, Y, and Z coordinates for these little cross joints. Grid 2 onto the SOP. You got it? Okay. Now we need to make a new table DAT, and it's going to be completely blank. Now I'm going to pick up this table DAT and drop it on the DAT2. So the way that this pipeline works is we take our grid, turn it into data. Between here, we're going to manipulate the data slightly and put it into this table that then turns it back into geometry for us. But the first thing we need to do is I need to take a version of this table and put it in here so that I can then start changing things. So I'm going to make a new text DAT. I'm going to write a little bit of code. So you can program inside here however you want. Because I'm not using the geometry window in the top right, I'm going to click the little triangle and turn that into a text port so I can code in here. I'm then going to right-click that new blank text DAT and say Edit and Textport so it appears in the top right. Now, thankfully, in Touch Designer, there is something called a copy command for DATs. So I can say, literally, this table become a copy of that table. And to do that, I say operator table 1, so the output table, dot copy the original table, which is called SOP21. So operator table1 dot copy operator SOP21. And if I've spelled everything correctly, and I right-click run this script, what we'll see is a version of an exact replica of this table appear in that table. And this is effectively a reset button we've just made. So if we make lots of changes and for some reason it all goes wrong, we can now rerun this to always make a copy of the original grid's layout. So what we've just made is an exact copy of our original grid and effectively becomes a reset button. What we need to do now, is turn all of these data points into physical 3D points. So I'm going to make a new comp geometry. Actually, ignore that. No, I'm not. First, I'm going to make a SOP circle, excuse me. So SOP circle. SOP circle. So we're making a flat, round shape. We are then going to add that to a transform SOP. Then we're going to add a material SOP, null SOP, and then finally right-click geometry. So circle to transform, to material, to null, to geo. And then once you've made that, in the new geometry, go to the Instance tab and turn on instancing. Now, when you enable instancing, the first thing you need to do is reference data. So we're going to take table 1, that one that we just made and copied everything into, and attach it to instance chop.sop in the Instance tab of the geo. Now I'm going to assign the parameters for the instances by clicking the little triangles at the end of each row. So I'm going to set translate X to P0, translate Y to P1, and translate Z to P2. And then, as with everything else we've done in this scene, we need to parent it or child it to the null at the top that controls our scaling. Now, on the right-hand side, everything should go black, but we should see our grid. And that's because we basically got however many points there are. I think there's like, let's have a look. So we now have 64 giant dots covering our image underneath. So we are going to first change its Z's translate to be 2. So it's the furthest forward thing in our scene. And we're going to change our uniform scale down to about maybe it's in our transform we want to do it. Yeah, so in the transform SOP, not the geometry transform, we're going to change uniform scale down to about 0.01. And you should have lots of little black dots on all the crossing points inside our grid. There is a problem with our circles, though. If we look at them, they're slightly oblong. And that's because we have a circle of scale 1:1 being translated into 1920 by 1080 space. So we're going to do the inverse
of the aspect ratio translate that this null is doing to our spheres before they become instants. So inside the same transform SOP, I'm going to go and get the aspect ratio that was in1.aspect. But in the X, I'm going to get the height, if I can spell it right. And in the Y, I'm going to get the width. So I'm basically going to get the inverse aspect ratios from the scale that we're applying at the top. And you want to divide them by some arbitrary number like 10,000. 10,000 might be a bit aggressive, so 1,000 seems to work fine on my scale. So the circle into a transform. That transform now has a scale of aspect height divided by 1,000, and its Y is aspect width divided by 1,000. So effectively the opposite of the scale we're applying to it at the end. And now it's a little cosmetic thing. That just means we have a perfect circle. Now, again, cosmetically, we're going to give that a texture. So make a constant top. Pick your favorite color. And then apply that to a constant material. And apply that constant to the material tab. So now I have lots of little red dots. And what we'll do is we'll take another 5-minute break there, just so that we can catch everyone up. And we can go for the final home run of making this work. So what we need to do now is we need to build a system that lets us pick up these points, move them, and then store where we put them down. So what we're going to do for that is we're going to use something called a render pick that allows us to look at what the renderer is seeing and then tell us when we're colliding with geometry in that by basically sending a ray from the camera to wherever the mouse click is. But the very first thing we need to do so we can do that is we need to isolate just the points in the render. So we're going to right click, I'm just going to double click in a blank space and add a render pass. Drag and drop or connect the render one to that render pass, but change the geometry from an asterisk to just be Geo3. And then click clear to camera color. So render pass, change the geometry so it's only referencing our dots, and then enable the clear to camera color. And what that's doing is it's going to that camera and doing basically isolating the dots from the renderer. So we just see our dots. Now we're going to double click and add the DAT called render pick. Now the render pick is really brilliant, but also really fussy. So it needs very specific parameters passed into it before it will even start to work. And those parameters it needs, if we go to the chop tab and search for panel, now the panel is going to give us loads of information from the container that we're inside of, like mouse position, what I'm clicking with, how many times I've clicked with. But we're going to isolate them down to just the U, the V, and the select. So inside here, instead of asterisks, I'm going to type U space V space select. And that's going to give us just our U, just our V, and whether the mouse is being pressed or not. We need to turn them into something the render pick will understand. So we need to turn them into a DAT. So we're going to go to the DAT, get a chop 2, drag and drop that panel onto our chop 2. And then in the chop 2 DAT, make sure we enable the include names tab. Connect that to our render pick. and then grab that render pass we made and put it into the render pass top. So now, if you click on one of our dots in the panel, what we'll get is a reference to Geo3 out 1, so the instance. You need to go and get the render pass and put it into the render pick top parameter up here. Do you have include names turned on your chop 2? Chop 2 needs to have include names turned on. Okay, now this information alone is useless to us without the actual instance of the dot that we're getting. So on the render pick, in the options tab, we're going to turn on fetch instance ID. And now when we click something in the panel, it's going to tell us a number. And that number relates to the row that this dot was drawn by. Okay, so now we're starting to get enough information to be useful to us. But if we look at the panel that we made when we got U, V, and select, we'll notice that if I put my mouse over the panel, nothing happens. Those numbers don't update. But if I hold the mouse down, they do update. Now, this is to do with the way the panel works, where the U and V are basically the X and Y coordinates that you are inside that panel, but they only update when the mouse is interacting with it. We can get another version of these called roll U and roll V that update continually until the mouse is clicked. So we're going to have to do some messing around with values that basically says, get where the mouse is based on the roll values until it's clicked, and then update from the U and V values once the mouse is being clicked. Excuse me. So, first thing I need to do is as soon as the mouse is clicked, I want to store this instance number. So I'm going to make a chop constant. I'm going to call that selection. And I'm going to change chan1 to be instance. Oh, no, I'm not, obviously. Instance. So now I have a constant called selection that has a channel called instance. And we're going to reformat the way that this is built quickly so that render pick is always updating where the mouse's location is. So I'm going to change the render pick, the panel, from getting UV select to just getting roll U space roll V. And now our render pick's going to get super upset because it's not seeing those 3 important channels. In the rename column or rename row, I'm going to change that to U space V. So now the panel is giving me the roll U and roll V values. So if I'm inside and move around, the numbers update. But it's changed them to just be U and just be V for us. And now we're going to brute force the selection parameter. So we're going to make a blank table. I'm going to activate it and right-click and add a row. In 0, 0, I'm going to type select. Below that, I'm going to type 1. So we're basically faking the select column. So that's a blank table, activate it and right-click, add row, select, and 1. And then we're going to add a merge dat. I'm going to connect both my table 2 and my chop 2. And how needs to be changed to append columns. And now we'll get that trio again that is select, U, and V. U and V are going to continually update when the mouse is inside the window. And select is always going to be 1. So if we pass that to the render pick, whenever the mouse is over an object now, it's going to return its value. and most importantly, its instance.
Can you repeat after that with your table and the
So,
merge?
so add a table. Do you have 2 rows?
Yeah.
So name the top row select and the bottom row 1. Click on merge. And then append columns. That one, yeah. There you go. So once you've got your table with select and 1, merge them in a merge dat with append columns.
So what you do here is define a list of commands. And in this case, I have and it's called show, and it's going to always call self out. Right? So what happens here is that if that comes in here, it's going to say, oh, we found it, and then it's going to say run self command, which is this.
Okay, so we move our mouse, and then anytime we're over a point, it gives us its location and instance. I'm going to add the next bit, then I'll stop and come around and make sure everyone's there. So don't worry if you've lost part, just stay as up to date as you can so that we can keep moving on. I'm going to double click and add a second panel chop. And this time we're going to do the same as we did before. So I'm going to get U, I'm going to get V, and I'm going to get select. So I have one version of the panel that's always updating and faking a mouse click. And now I have a second version that when I click the mouse, it activates and gives me the U and Vs. So this top one gives us the instance that we're over. And this one is going to be used to basically say, okay, if we're over a dot, then click and drag it. And we're going to do all of that with a chop execute dat connected to the second panel that we made. Now, by default, the chop execute has value changed on, but we don't want that. We want to disable it and click on to off, while on, and on to off again. Or sorry, off to on, while on, and on to off. And we're going to change the channel from an asterisk to just be select. So now this chop execute will only run functions when the select channel is either on to off while it's on, or if it turns off again. And now I'm going to right click and edit in text port so it appears in the top right. So what we need to do first is we need to store the instance that is potentially being clicked. So as soon as the mouse is pressed and select becomes 1, we're going to go and grab the instance and put it in here. So in off to on, I'm going to type operator selection dot par dot value 0. So we basically want to go to the selection, the chop called selection, and place a value into its first parameter value, which in this case is instance. And we're going to set that equal to operator render pick 1 row 1. So that's 1 comma, and then I'm going to do instance. So what will happen is anytime the mouse is clicked, it will go and get the instance of it will go and get the instance value from this table here. So on to off, go to the selection value and make it equal to whatever the instance is. Now we need to add a little condition here, because if it's -1, we don't want to pass that anywhere. So above that line, I'm going to write if operator render pick 1 row 1 column instance does not equal -1. Semicolon, and then tab the selection line in. So this little piece of code literally says, as long as the instance number is not -1, we'll update the selection table. Now, you should be able to test this is working. If you click in the table, nothing will update unless you're on top of a little dot where the number in your chop will change. If I can actually get my mouse over them. And then when the mouse is released, we need to update that selection chop to equal -1 again. So as in, make this redundant. So I'm going to copy this whole line and paste it into onto off. And instead of render pick, I'm going to make it -1. So all that guarantees is as soon as the mouse is released, this number becomes -1. But as soon as I pick up a dot, it becomes the number until I let go of the mouse again. So everything is default. We just enabled fetched instance ID. Okay. So now we've done that. We've set all the groundwork up. What we need to do is now take the value of where the U and the V is and pass it in to our original table up here. So table 1. So what we're going to do is we're going to work out which instance is being picked thanks to this. We're then going to go to that row in that table and then update its P0 and P1 position based on where the mouse moves to. But the thing we need to remember is it's giving us an instance ID based on a row number. So for example, if I click this, which is 0, row 1, index 0, if I click it and look at the number of instance it gives me instance 0. So I need to bear in mind that although I'm getting instance 0, it's on row 1 in that table. So we're going to need to remember to add 1 to the index we get so that it runs properly. Now this is going to be a bit of intense programming, so I'm going to write it or talk it, write it, and then I'll come around and make sure everyone gets it, because this is effectively it at this point. Once we do this piece of code and it works, we will have a pixel mapping device. So while on is only going to run when the select panel is 1. And the first thing I want to check is I don't want it to do anything if instance is -1. So I'm going to do the same if statement from above. I'm going to write if operator, but this time I'm going to say selection channel instance does not equal -1. So only run this code if any number other than -1 is inside here. First thing I'm going to do is I'm going to get U. And U is going to be equal to operator panel 2. U. I'm sorry, I'm going to say U is equal to. Then I'm going to get the V in the exact same way. So I'm going to say panel 2. V. So now if the select is held, so the mouse is held, and this number does not equal -1, it's then going to come into panel 2 and get whatever these values are. Now, we're working between texture coordinates and 3D coordinates here. So U and V go between 0 and 1, but our point positions go between -0.5 and +0.5. So we need to normalize or adjust these. So I'm going to say norm, and I'm going to say U is equal to U minus 0.5. I'm going to say V is equal to V minus 0.5. Finally, I'm going to then put them into the table. So put into table. So we're going to first go to the operator table. So I'm going to say operator table 1. I'm then going to go to the row that is operator selection instance. Now, when you pull data from a table like this, it comes out as a float. So we're going to wrap that in an int call to basically remove the 0.0 from the end of it. And then remember to add 1. That was what I said. We need to get our instance and add 1 to go to the right row. So this entire section here, int operator selection instance plus 1, goes to this table, finds the right row for the dot that we've selected, and now we need to update its U. So I'm going to say P0 wrapped in parentheses. So it's going to go to this column and set it equal to whatever we made U. And I'm going to do the exact same for V. And V being the Y coordinate. So it's going to be P1 is equal to V. So we now have a loop. We're constantly reading the panel so that when the mouse is over a dot, it gives us its number. If the mouse is clicked, it then stores that number and gives us it as an instance. Second the mouse is released, it resets it to -1. We do that purely for the reason that if it stored the instance number and we clicked somewhere, we'd start snapping points around. But now we can pick up points, move them, and we're able to displace them in the table. There is one issue though. Visually, we're working at a 1.1 scale. So what we need to do is we also need to multiply the numbers that we're getting by the inverse of that. So between the normalize and putting them into table, I'm going to scale them back to the original by timesing them by 0.9. So I'm going to say U is equal to U times 0.9. V is equal to V times 0.9. I might have actually times these by the wrong number. It might be 1.1 we need to do. Yeah. So now when I click a dot and move it, it doesn't snap. It actually goes to where it should be in relation to our mouse's coordinates. Okay. So now we have a grid. We have a real dense grid, and now we have points that we're able to move in 3D space. The one final thing we need to actually do with this is use the low resolution grid to update the high resolution grid. To do that, we're going to come back up to our two grids. Between grid 1 and material, we're going to insert a lattice. Now, a lattice allows you to, it's meant for animated deformations, but we can use our two grids to manipulate the big dense grid. Grid 2 goes into the top one. Dat2 goes into the bottom one. Its deformation type becomes points. And the radius you can play about with, but normally changing it down to about 0.3 or 0.2 means that now when we move these points, our grid will deform underneath it.
Yeah, with the...
I don't know how I did that by mistake. Okay, that was a bombshell. So if you've really messed up your grid and it seems broken, you can go back to the original table and rerun the text script to build it all again. Okay. So I know some of you still have some errors, but there's one part I want to show you just before we finish up, and then I'll stick around and we can clean up anything that's still not working. And that's ultimately we've made a mesh that we can deform and then project. That's fine. But on our top level, we need to find a way to properly blend them together.
Define a list of commands, and in this case I have and it's called shells, and it's going to always call self out. Right? So what happens here is that
Around, you know, a 30% overlap. So we'd never set up our projectors up like this. We would move the image all the way so that only around this was actually being overlapped. And then what we'd do is we'd use the exact same tools that we built in our rough map to then basically blur the edges into each other. So if you copy and paste rough map and then go inside of it again, I'm going to reset my table. And then I'm going to make sure that I update my panel to be looking at the new rough map I made. So right now, I'm inside an exact copy of everything we just made, and I reset the grid. But now we don't so much need the complex grid points. We more just need to be able to move the edge off our image. And to do that, I can replace my grids with a rectangle and plug that into my material. And we're using, because we don't have such a complex grid anymore, we can actually use the same master rectangle to control both parts of our geometry. So we no longer need the lattice. So I just have a rectangle that goes to where my material was and into the DAT2. If I connect that new rectangle up to my SOP2, you'll see I only get a table of 4 points. Now if I rebuild everything, I'm given this, which works the same way. You can move these around and you start to get a kind of corner pin. But what we actually need to do with this is apply a material over the top that we're deforming instead. So my in image is going to go to my out image. And the camera that's capturing our output is no longer going to see this, but we're going to make it see a blank white constant. So now, if you connect the DAT2 into the material that's got the white on it and the material that's got our wireframe on it, I now have a square shape that I can move around. I want to make it slightly more complex. So between the first rectangle and my DAT2, I'm going to insert, what is it called? Resample. And then that resample is going to go to our DAT. Now if we rebuild our table, we have way more points that we can move for a much finer adjustment. And the last thing we need to do is composite this image here over the top of the image in. So I'm going to multiply them together. And what that gives us is basically a masking tool. Nothing more complicated than that. So now all that's being shown is the area that's still exposed white. And to initiate the blend over them, between the output and the multiply, we insert a blur. Now, the higher the blur, the more intensive it is going to be on your computer, but it builds the bridge that allows us to blend the two projected images together. So now on our dome, if we connect these two together, means we get our warped image and then our masked image. Unhappy about something. Let me just check where. Oh, I've not connected it to the out. So now it's outputting a warped and blend masked image that in our dome has the soft edge that we could then pair both projectors with. So I will put, I appreciate we ran out of time towards the end, just when we got stuck on the little issues. So I will put this file up for us. I'll build out the two mappers for us, so the rough map and the mask, just so that you have a reference if you want to continue building it. And then obviously I will stick around here for undoubtedly the questions that you have now that we're at the end. Is there anything specifically anyone can think of at the moment that they need to ask?
What's the procedure for like setting this all up? So we place our projectors first, and then do we align them like in there? Or?
Really depends on how you want to build it. Like sometimes in the domes that I showed you at the start, we knew precisely where our projectors needed to be to map them, so that we kind of knew values that we would put into the X and Y and Z for the position in the viewer. But ultimately, you can kind of just eyeball it all. And then these tools, the rough mapper, I would then suggest you build a fine mapper that has a higher density grid, allow you to move them where they need to be. So it really depends on the situation, but if you're building a dome yourself, I'd build the physical structure, work out where you think roughly those projectors are in that dome's virtual space, and then put them in place. And then all you would do is then send this null, that is the output from that projector, to that projector in perform mode, and it would line up.
Does it matter if the dome is not perfectly like semi-spherical?
No, not at all. So the fact that we built the system like this, all it's doing is capturing from its own surface. So if your surface is also deformed, like we made the sphere a weird shape, for example, we would still capture that weird shape. If I set this to, so you can see it changes how it actually captures. So Z means it's deeper, so it looks like it's more stretched, but it's just because it's seeing a much larger section of that curve. So the system itself will compensate for that. You can even load something like geometry in here, and it doesn't need to be a dome. You could projection map onto anything with this technique. It's just really good for domes. Anyone else? Okay, perfect. As I said, if you keep a hold of that Dropbox link, I will put this file in there right now, so you can go and download it right this second. I won't put this version in. I'll actually put a more complete version in that has like a performance mode built for you as well. Okay, yeah.
This is the warbling. It's essentially a content mapper, but simpler.
Yeah, I think another example is really similar to how Stoner works, but we have more control over what we can and can't do. So with this, as when we control how the points are moved, we can actually start storing things like undo buttons. And as I was talking about, disabling the render pick is a really important thing that we can't do with Stoner out of the box. Stoner is something that's in the palette browser if you're not familiar with it, but it's like a keystoning tool for projection mapping. But yeah, very similar to how Cantan Mapper works, but with, I would say, slightly more control out of the box. Does someone have something up here? Yeah.
Can you put that Dropbox link up on the screen again?
Sure.
Also, if you were going to use like a calibration tool for your projectors instead of doing this, do you have one you recommend that plugs in?
As in something that automatically calibrates a whole dome.
Like if you have like 24 projectors, you're trying to do one of these things.
The one that we used prolifically is called Vioso, V-I-O-S-O. It has a top built into touch. Basically, you use their software with a special type of camera. It builds meshes that you then apply textures onto. So basically what we did with the points, it builds in 3D for you. That and there's another one called Scalable Displays. Both have texture tops built in. They are super expensive though. Vioso is a per channel license. So if you have a 24 projector dome, it's about 4,000 euros per No, sorry, €1,000 per projector, I think, is the ballpark cost. So that and a camera that could see is probably about $30,000 you're spending. Yeah. But it would be much quicker than building 24 of these, let me tell you that. Yeah, we ultimately moved over to a completely automatic calibration system, mostly for when someone's unfamiliar with the system like this, not positioning the virtual projectors in the right place causes chaos. The more work you put in getting your projectors in the right place, capturing the right field of view, saves you a lot of time in projection or pixel mapping. But if you don't do that and say you've got someone on site setting up for you that doesn't know that, it can be chaos. So basically they're having to try and fake the entire image rather than capturing it naturally like we are doing here. But yeah, ultimately we moved over to a fully automatic system. Cost-wise, I mean, you kind of pass it down to the client is the end result. So it depends on who's buying and who's willing to pay, but it makes the user experience much easier. Sounding like, yeah, there is a top that can load their bespoke file. Basically, yeah, it's always been my dream to try and develop an automatic calibrator in touch. It's just, well, time is a big problem, but there's a lot of complexities in seeing. They take pictures of loads of different patterns and then turn that into a mesh that I'm just not smart enough mathematically to do, is the honest answer.
Setting up the projectors, like, is it good, like, to get out your protractor and be like, this is at this angle and this is at this many feet away or whatever?
In my experience, eyeballing has been more than enough. It's just, if you're building a system where, let's say, like this camera, for example, it's sitting on the edge of my dome pointing in. But if someone had positioned that so it was up here, and then I was starting to rotate it down, so my virtual camera is up, but my real camera is forward, it starts meaning that anytime I pixel map, I'm having to pull everything down. So as long, eyeball is okay, protractor if you want to, but you're never going to get it that close. Like, yeah, that's probably where you would start. And so you would have it set up in the basic projection mode, so you'd have none of these grids manipulated. Then you just throw the straight image onto the dome, get as close as you possibly can, and then it's fine-tuning is what these tools are.
How would you recommend for several projectors edge blending together? Because like this kind of works for 2 projectors, but when
so
multiple.
Ultimately, when you get to more complicated projectors, so let me see, do I still have that? If I load back up the About Me stuff, I think I've got the image I used to market this. I just want to talk through, because that's kind of a more real-world example where I think I have 4 projectors. Yeah, so this is only 2, unfortunately, but yes, you could do it, but you need to start thinking about them in terms of 2D canvases being projected into a 3D space. So if one of the domes that we worked with, so it's round and it's 90 degrees, so this is standing up straight. And what we did is we had projectors here and here, projecting into the dome and then into the opposite roof. So this one did that side and this one did that side. And that left us with a canvas that was basically 4 projectors. And our bottom ones would kind of look like what we've been experiencing today, where they kind of look like a curved away from the image. But our top one would be almost like a pizza slice. Now in here, it's all about just getting that, I keep saying 30%, but that's kind of what everyone talks about. So really making sure that this edge here, so this is blended out here, and this is blended out here. So you use the mask at the end of it to basically stop any of this ever being rendered. So it is definitely possible. I have experience doing it with 4 projectors like that. It just takes more time. So you end up in the dome, when you see it, like a pizza slice here and a pizza slice here, and then two big squares at the bottom. So you're only having to blend that edge and then the middle between the two top ones. Because the more curvature in what you're projecting, the harder it gets to blend, because you're trying to do it with a straight line and a 3D space.
And then the opacity difference, how would you count that in?
So the blur itself will have a fixed amount that we can't calculate. I don't know a way to calculate how much that blur is.
So you can't do like this quarter has 3 projectors on top of each
Yeah.
other. Let's set that to like 10% or whatever.
So you could try to do that with the channel mix, but you're probably going to run into more problems than just trying to basically get your two pizza slices next to each other and then letting the blend do it.
Okay.
You can end up with sort of slight hot spots and dark spots if your image is off, but you can then just keep increasing the blur width until you get to a position where you're comfortable with it.
Okay.
Content plays a big part in what you're showing as well. So if you're doing like a typical planetarium has a lot of dark imagery, so normally you'd never even see it. But if you're displaying pure white content, you're going to notice those hot and dark spots really, really badly.
Yeah.
Anyone else? Okay, again, I'm sorry we ran on a bit at the end. It's just way more complicated when you try and talk it out loud. Again, I'm definitely hit me up with questions if you have any more. And if you need help or you do want to continue building this, please just let me know where you're at with this file, and then I'll help you continue adding to it if it's something you do want to use practically. Thank you very much. Let's go and get some lunch.